Okay, so now let's get to the second step in proving a theorem that uses quantifiers. What we want to do is migrate all the quantifiers out to the front. Now, because of the first step, which was renaming quantifiers, we're guaranteed that all the quantifiers are talking about different variables, okay? So we're not going to have for all x and for all x in some other spot. They're all different variables. So here's what we want to do. We want to take something that's like this, that has this quantifier, this one, and that one, and we like to move them all to the front. And notice in particular that what I have here is one very large expression, okay? That if I look inside, that there are absolutely no quantifiers, okay? Because everything's being migrated to the front. So it's not just to the front, it's outside of any logical connective. So if I have an implication and the implication says something implies that there exists, oh no, that has been moved out. If I have for all x something, that implies, no, the for all x is all the way in front, meaning above, if you will, the implication, right? So that what I'm left with is an expression that has logical connectives but absolutely no quantifiers. Okay, so here's our first rule, and I call it and all right? And so what we have is we have an and this is in the left-hand side of an entire expression which is ended with something else, okay? So I want to be very clear as to the ordering of this. There is a for all, and something that the for all is actually quantifying, right? And that is an expression that I then and with something else, okay? So it is this this for all and this and that kind of named this rule, okay? And I want you to realize that the for all is like immediately below the and, okay? So we have for all something, parentheses, and something else, okay? So that's when this applies, and what we'll do is we'll simply take this and move it out. So you see here, this and just came here, and now the expression that that and is quantifying over the for all is anding over actually includes that and, okay? So that's the way this rule works. One thing to note is that the P of y is now inside of the scope of the for all quantifier. This could be a really big mistake if that P of y term actually contained any x's, but we know that it doesn't because we've renamed all the variables, right? So that's why it's so important to rename variables at the beginning. All right, let's take a look at our next thing. And we now want to have and there exists, okay? So this is similar to what we had before, and again, there's an and which is joining two terms, and the first of those terms actually has there exists at the very top. And just as before, we'll simply take that there exists out, and now it's going to quantify over the entire expression, including the and, okay? So again, this only works because the term on the right-hand side, which was P of y, can't possibly have any x's. So now let's try negation, okay? And negation is a little bit more interesting. So we have a negation of a term which immediately includes a for all, okay? So for all is like the first thing that you encounter inside a negated term. So what we'll do is we'll take it outside of the negation. So now we have a quantifier and then negation. But the quantifier has flipped, okay? So for all has become there exists. Now, think about that. What I really had was not for all, and it has become there exists not, okay? So what we're saying is that it is not true that all x's have some property. Well, if that's the case, then there must be at least one x that doesn't have the property, right? And that's exactly what this move does. When I take the for all above the negation, then the negation essentially flips it, because it is not true that that for all something, that means that there exists an x that is a counterexample that doesn't have that property. If I have not there exists, then the same thing applies. What will happen is that the quantifier again flips, so there exists becomes for all. And as before, what's really happening is that not there exists means the for all not, okay? So if there does not exist some value that has a particular property, okay, then that means that if I look at all values, none of them can have that property, okay? So that property is just always false. And that's what this says, right? So again, negation actually flips the quantifiers. None of the other ones do that. Okay, so let's look at implication, right? And actually, implication is it's just a shorthand for not A or B, right? So really, we don't have a choice. We already said what happens with not. We already said what happens with or. So we should just have to follow the rules that we've already established. Okay. So let's see what we have here. Here we have for all x, p of x implies something, right? So be very clear that the for all is inside the left-hand side of the implication. Okay. Now let's see what we've seen already. Okay. What we have is that this is the same thing as saying not for all x p of x or q of x, right? That's just following our rules, right? So this, rather the implication here, okay, has been turned into a not or, okay? And like I said, at this point, my hands are tied. I have to do exactly what I'm supposed to do. So let's see. Okay, that means that there exists an x such that not p of x. How come? Because not for all is the same as there exists an x not, right? So I didn't have a choice. That becomes that. And the there exists is in the hypothesis, but I can now migrate it out, right? Because I can migrate there exists from an or. So that's now become there exists an x such that not p of x or q of y z. And notice that at this point we're done because in fact that is the implication of a term, right? So we started with this. We had a for all quantifier that was inside an implication. And what we did was we pulled the for all out to the front, and so now the implication is inside the quantifier, right? But when we pulled out the for all, it became a there exists. Okay. This might seem mysterious, but it's really not. The hypothesis of an implication is negated because it's not A or B. And when we pull out the quantifier through a negation, then it flips. Okay. So if you believe that, you probably believe that if I take a quantifier and that's on the conclusion and pull it out, that in fact it won't flip, right? And that's exactly what will happen. Okay. The for all x here is actually not going to flip at all because not q or p now is an or for all, and or for all, I simply take the for all out in front. I'm left with a not q or p, turned out back to an implication, and I'm done. Okay, so this quantifier actually migrates all the way to the front without flipping because it's in the conclusion of an implication, and the conclusion is just or, right? It's only the hypothesis that needs to be negated as well. Okay, so if you look at there exists, it's the same thing that's going to happen, right? So if I have it that there exists on the implication, then when I pull it out, it's going to become a for all. Why? It's just going to flip because of the not in the implication. On the other hand, if it's on the conclusions, then it's going to come out and it won't flip because in the conclusion it's just or. So make sure that you can do the proof for that, okay? It's exactly like what we've seen in the previous slides, so really you shouldn't have any difficulty with that.